Hello, this is the third video in the series about physical and chemical properties of seawater. Today, for this video, I'm going to be talking about the physical properties of pure water. Okay, so the physical properties of water. So, water's chemistry affects its physical properties as well. For example, water has extremely high surface tension, highest surface tension of all liquids in fact. And surface tension is the ability of a liquid surface to resist an outside force. And I'm going to go through each one of these individually as well. Water has a higher specific heat capacity and latent heat than all liquids except ammonia. Water has a very high transparency. Ice is less dense than water. And water can dissolve more substances than any other liquid. Okay, so start out with water's high surface tension. So water molecules stick to other water molecules. This is called cohesion. And water also sticks to other materials. That's called adhesion. So when things are cohesive, they're very tightly joined together, right? When something is adhesive, it is used to stick two materials together, right? You use an adhesive to, like glue. Glue is an adhesive, okay? So water will stick to other materials that are polar or charged. And again, that's because of water's molecular structure and that it has a negative side and a positive side, which means that it can stick to anything else that has a negative side and a positive side, or that is overall has a positive charge or has a negative charge. Okay, so water's high surface tension is the reason why some bugs, specifically these water striders, can actually walk on the surface of the water and not sink down through it. And it's also the reason why, the combination of adhesion and cohesion is describing this image right here. So water has a strong surface tension, which means that the paperclip can float on the surface of the water. And also, water is adhesive and cohesive. So it's holding on to the sides of the glass and it's holding on to itself. And that's why the water can actually go up above the rim of the glass slightly and not flow over the edge. Okay, now I'm going to play a video for you. If this doesn't come out clearly, there is a link on the under the module, the same content page that you used to get to this video. There is a link to the video that I'm going to show. So if as I start to play this video it's not coming through well for you, then just go to the link and watch that and then pause this video and come back.
Truly amazing. Water, the most common substance on our planet, the universal solvent, essential for life. Its unique properties come from its atomic structure, a compound made of two hydrogen atoms and one oxygen atom, symmetrically aligned to look much like mouse ears. This structure is responsible for many of water's properties, including water's ability to stick to other objects and to itself. Cohesion is the attraction that occurs between a liquid's molecules. This attraction is caused by a difference of charge. The law of electric charges states that like charges will repel and unlike charges will attract. It is this law that governs cohesion within liquids. It turns out that a molecule of water is not completely neutral, but it is said to be polar. Due to water's symmetry, the oxygen side carries a more negative charge, while the hydrogen side carries a positive charge. Thus, water molecules will attract at opposite poles, causing this property of cohesion. This cohesion is the cause of surface tension, which is the amazing ability of the surface of a liquid to exhibit unusually stronger intermolecular forces, and thus can allow for the suspension of objects that normally would not float in water. This extra cohesion happens as the result of surface molecules having less neighboring molecules to attract to, and thus they will attract to each other with much greater force. Adhesion is another property of liquids. It is the ability of a liquid's particles to attract two different particles. Look closely at this water in a container, and you'll notice that it seems to climb up the walls. Adhesion plays a role in the creation of a meniscus in a graduated cylinder. Water will climb upwards in a straw because it is attracted to the straw's walls. This occurrence is known as capillary action and plays a major role in our everyday lives. One way to demonstrate water's attractive ability is to negatively charge a balloon by rubbing it with fur. Watch the stream of water attract to the balloon as it is moved nearby. The negative charge of the balloon will attract the positive hydrogen atoms in the water molecule, and thus the stream attracts the balloon. Capillary action allows plants to draw water into their roots and transports the water through them. This experiment with celery shows the transport of blue-colored water through the stalk and into the leaves. Both properties of cohesion and adhesion together are responsible for some of water's most unique behaviors, its ability to stick to itself and to other materials as well. Consider the drop of water. What makes droplets anyway? The answer is cohesion and surface tension. Notice how water can hold itself up against gravity, giving the drop height. Compare this to alcohol. The alcohol spreads easily and cannot hold itself up against the forces of gravity. Water's cohesion is stronger, and thus, so is its surface tension. Mercury is a very unique liquid, also known as quicksilver. Mercury has little or no adhesive properties, yet it has very strong cohesion. Notice how the mercury can move on the paper surface without sticking. Even attempts to break a drop-up sometimes fail. When left on its own, we can see the small drops of mercury attract. Many recombine to make larger drops. Mercury particles are attracted as the cohesive forces prevail. Mercury's strong cohesion is responsible for the convex meniscus it forms in a graduated cylinder. Water, alcohol, and mercury are each three liquids that have different degrees of cohesion and adhesion.
Okay, so in the video we saw examples of adhesion and cohesion, as well as some other great examples of what happens when two things attract, such as when they had the balloon and brought it towards the water was attracted to the negative charge on the balloon. So which side of the water molecule do you think was attracted to the negative side of the balloon? you should have said is the positive hydrogen side, because the opposites attract, right? So the positive side of the water molecule will attract to the negative balloon, negatively charged balloon. So in this image here, we're showing you what cohesion means and what adhesion means to give you a better idea, maybe a visualization that might help you to remember. So here we have two water molecules. They're spread across the top of this container. So imagine that this whole container is a tube or such, and it's full of water molecules. And we're just seeing two water molecules up here at the surface. There's one water molecule, here's another water molecule. They are cohesive, so they hold on to each other, right? And so that makes it so that they, actually, let me get to that in a second. So they're cohesive, so they hold on to each other. They're adhesive as well, so they hold on to the glass. Okay, so they grab onto the glass, and when you look at the side of a glass and it's not all the way full, you'll notice that there's a curve. We call that the meniscus, so there's a curve on the water, and that's because it's grabbing onto the edges of the glass. It's like kind of climbing up the edges of the glass. And if your glass tube is small enough, then the water can climb up quite high, which is why if you put a straw in water, you'll see that the water level in the straw is actually higher than the water level in the container that you have. Now, what I was going to say, I was going to describe the surface tension for you. So imagine that you have this layer of water molecules, and then you have another layer of water molecules, and another layer of water molecules. The water molecules underneath here, they can grab onto these ones, they can grab onto the ones underneath them, they're grabbing onto the one next to them, and they're grabbing onto the glass. Whereas the ones at the surface can only grab onto each other and the ones underneath them in the glass. So the force between them and the glass is actually stronger, and that's what causes the high amount of surface tension. Okay. Water is also highly viscous. This is kind of just a side note. So it's highly viscous in certain regards, I should say. So viscosity is the ability of a fluid to resist flow. So water compared to syrup, water would have a low viscosity, and syrup would have a high viscosity, or syrup or honey, right? So what that basically means is water will flow more easily than syrup will. But if you compare the viscosity of water to that of, say, air, then water has a much higher viscosity than air does, right? It's much easier for you to walk through the air than it is to swim through the water. So there's also a temperature effect on viscosity. I'm sure that you guys have probably had experience with heating syrup or heating honey. So what happens to it when you heat it up? Does it flow more easily or less easily? Or inversely, if you cool it down, does it flow more easily or less? So when the substance is warmed up, that actually decreases its viscosity. So it makes it more easily flow. When a substance is cooled down, it makes it more viscous and more difficult to flow. Okay, so when organisms move through a substance, the size of that organism matters to how easy it is to move through that substance. So, who do you think moves more easily through the water? Do you think that it is this little copepod, which is plankton, so it's a tiny little organism? Do you think it's a human being? Or do you think that it's a large whale? If you answered whale, then you are correct. So for small organisms, when they're moving through water, to them, it seems more like they're moving through honey. So they kind of jump from place to place because it's very difficult for them to move through. It's like, imagine if you had to move through honey all the time. Whereas, as compared to us, a whale is able to move through the water much more efficiently, much more easily, and it doesn't feel nearly as viscous to that whale because it's so much larger than we are. Okay, would it be easier for plankton to move through water or air? You should have said air because air is less viscous. And would plankton sink more quickly in warm water or cold water? And the reason why this is important is because lots of plankton are photosynthetic, and they rely on sunlight in order to photosynthesize. So since sunlight doesn't go all the way through to deep depths, then the plankton, the phytoplankton, would need to be floating at the surface. So would plankton sink more quickly in warm water or cold water? If you said warm water, you are correct. Therefore, they would need to have some mechanism to keep them floating more readily in warm water. Okay, water also has a high heat capacity and latent heat. So high heat capacity means it takes a lot of energy to raise the temperature of water. Raising the temperature of something means that you are making the molecules move or vibrate more quickly. So, and the opposite, lowering the temperature of something means that the molecules are moving more slowly, or vibrating more slowly. Okay, and movement is called kinetic energy. Water also has a very high latent heat capacity, which means it takes a lot of energy to change water state. And on, so going from a solid to a liquid or a liquid to a gas. So what that means on a molecular scale is that it takes a lot of energy to break hydrogen bonds, because that's what you're doing when you're changing state. When you're going from a solid to a liquid, you are breaking some of those hydrogen bonds in that ice so that you allow for the water molecules to move more freely. When you're going from a liquid to a gas, you are breaking all of the hydrogen bonds so that you have free water molecules. They are not bonded to each other. So therefore, high latent heat means it takes a lot of energy to break hydrogen bonds. Okay, and the importance of this is that it influences the climate, and in particular, close to the ocean. So if you live someplace along the water, like we do, our temperatures are very much influenced by our cold Pacific Ocean nearby, right? So the ocean can absorb heat without actually changing temperature, and therefore our temperatures tend to be more mild than if you were to go to the middle of the United States. Okay, if you compared the temperature here versus the temperature, say, in Nebraska, Nebraska is going to have much colder winters and much warmer summers than we do. Okay, so the climate near the ocean is fairly mild. We have a narrow temperature range. Okay, so this graph that we talked about in the previous video, it shows, remember that we are raising a temperature of solid ice to 0 degrees Celsius. Then we're adding energy to make that ice melt. And then we're adding more energy to increase the temperature of the liquid water. And then we're adding more energy to make that liquid water turn into vapor or gas. Okay, so when the temperature is changing, -40 to 0, or 0 to 100 degrees, or 100 degrees up to whatever, off the chart, that heat that's being used to change the temperature would be called specific heat. The heat that's being used when there's a flat line where the temperature is not changing, so from A to B or from C to D here, that is called latent heat. So latent heat is the heat used to change the state. So that's why, even though there's heat being added to the system here, the temperature is not changing, because the heat is actually being used to break hydrogen bonds. And since going from a liquid to a gas, you have to break all of the hydrogen bonds, it takes a lot more energy to do that. And that's why it's 540 calories here versus only 80 calories down here. Right? 540 calories to go from a liquid to a gas, whereas 80 calories to go from the solid to a liquid. And remember, we were only talking about 1 gram of ice. Okay, so this chart is showing you the heat capacity of common substances, and you should see that pure water is higher than everything else except for ammonia. So that again means that it takes a lot of energy to change the temperature of water. And if you were to take water and sand and put them both under the same heat source with the same amount of heat for the same amount of time, the sand would heat up a lot more quickly than the water would. Okay, and that's going to be an important thing to understand when we're talking about atmospheric circulation and climate. Okay, water is also transparent, which means that you can see through it. And what that really means is that light can penetrate through it. All right, and so I have two pictures here. I have a picture of a coral reef on the left, and I have a picture of a kelp forest on the right. So the coral reef, coral is actually a animal. It's an animal that makes a hard outer structure, and so this reef is built by these animals, and it provides all kinds of habitat to fish and all kinds of invertebrates and other marine organisms. So the reason why it's important that that light be able to get to the coral is that living within the coral is actually a type of algae that photosynthesizes. And without that algae photosynthesizing, the coral has a hard time getting the nutrients that it needs in the quantities that it needs to be able to grow and thrive. So if light's not penetrating through, the coral's not healthy, there's no habitat for the fish and the invertebrates. So that's a big deal. And then over on the right, we have kelp forests. Same idea, the kelp is photosynthetic, and it provides for the main structure of this ecosystem. So if light can't penetrate through, then we can't have kelp growing either, and therefore we can't have all the different varieties of organisms that live there. Okay, and then finally, ice is less dense than water. All right, density is mass per volume, which we have already discussed. It's measured in the units grams per cubic centimeter. So with all other substances, density increases as the temperature decreases. So in other words, the molecules contract as they get colder. Okay, and what that means is that for all other substances, the solid form is denser than the liquid form, and the liquid form is denser than the gas form. So in all other substances, if you were to put the solid into the liquid, it would sink. For example, if I were to take a solid cube of oil and put it into liquid oil, this solid cube of oil would sink to the bottom. Whereas the opposite happens if you put solid water into liquid water, right? The ice, will float on the surface. And this is because water reaches a maximum density at 4 degrees Celsius. Then it becomes less dense. So in this graph over here, we have density on the y-axis, increasing as you go up. We have temperature on the x-axis, increasing as you go to the right. All right, so if we actually read it starting over here at 10 degrees Celsius, as the temperature decreases, the density increases. You see that we're going up. Okay, so the density is increasing as the temperature is decreasing until we get to 4 degrees Celsius. 4 degrees Celsius is this dot right here. After we get to 4 degrees Celsius, once we continue cooling it, the density is actually decreasing. Okay, and here is 0 degrees Celsius, right? 0 degrees Celsius. So that's the freezing point of water. So that's ice. So if you have, if you have ice floating in liquid water around it, that liquid water around it is going to be more dense than the ice is. Things that are more dense will sink, and things that are less dense will float. And so therefore, since the ice is less dense than the surrounding water, it will float on the surface. And that's important because that means that lakes don't freeze all the way through in the wintertime. Instead, they only freeze on the surface. So what happens with a lake is that what part of the water of the lake is connected to the atmosphere, because it's the atmosphere that is getting colder. So as the atmosphere gets colder, it's in contact with the surface of the lake. So the water at the surface gets cold first. It starts to get cold, it gets more dense, and it sinks. And that continues to happen until the surface water is less dense than the surrounding water. So once the lake is about 4 degrees Celsius, as the surface water gets colder, it actually stops sinking. It stays at the surface. So the surface water gets colder and colder and colder until it freezes. And then it's basically a layer of ice that's floating on the surface and insulating the lower body of water from that cold temperature. And so the water underneath the ice is actually still free flowing, and so fish and other organisms in the lake can still continue to live and they don't freeze. So this graph is showing us basically the same thing as the previous one, except we have a couple of additional information that I think is important for us to really understand this. So again, on this graph, we have the y-axis is density, we have the x-axis is temperature, all right? And you have a green line and you have a red line. The green line represents other substances. So as the temperature, so we'll start over here this time. As the temperature is increasing, the density is decreasing, right? The line is going down, all right? The red represents that pure water. So if we go over here to 20 degrees Celsius, we see that this dot right here, A, it's showing in this box the molecular structure of that liquid water at 20 degrees Celsius. Okay, as we decrease the temperature over here to 15 degrees Celsius, this is what the molecular structure looks like. So you should be able to see that there are more water molecules in this space than there are in this space. Therefore, B is denser than A. Okay, now if we continue to decrease the temperature, we eventually get to this location right here marked C. That's 4 degrees Celsius, okay? So we go up to this box and we see 4 degrees Celsius. Wow, look at how many more water molecules are at 4 degrees Celsius than we're at 15 degrees Celsius. So this is definitely denser water than this is. But look at what happens as we continue to decrease the temperature. Now we're at 2 degrees Celsius, okay? This is what 2 degrees Celsius looks like. There are fewer water molecules in this space than there were at 4 degrees Celsius. Therefore, this, at 2 degrees Celsius, this water is less dense than the water at 4 degrees Celsius. And then we can continue to lower the temperature to 0 degrees Celsius, and now we see a very rapid decrease in the number of water molecules in the space. And the reason why that happens is because when all water molecules are bonded together, they form a crystalline structure, and which actually causes that the water molecules expansion within the water. Okay, so because they are more spread out, there are fewer of them within the volume. Remember that density is mass per volume. So mass really means how many water molecules are there, how many molecules in general are there in this given volume. And since this image right here, these images are all the same, we'll say the same volume, it's really just the same area because it's one-dimensional or two-dimensional. But there are fewer water molecules here than there are here. There are fewer water molecules here than there are here. Therefore, when you take ice and you put it on water, liquid water, the ice will float on the water. Okay. Water also has a very high ability to dissolve other substances. So what that means is that water can bond to other compounds that are polar or that have a charge to them. And when they bond with those other compounds, they actually pull apart the atoms. So water molecules will surround those other atoms and bond to it. And in that way, basically breaking up the compound in the water. So that's, what happens when you add Alka-Seltzer to water. As long as you have enough water in there, you stir the Alka-Seltzer around and you don't see it anymore. It's dissolved in the water. Same thing as if you took a cup of water and you put a teaspoon of sugar in it and stirred it up. You wouldn't see the sugar anymore because it's dissolved into the water. So it's no longer visible. Sorry, let me go back to this again. before I finish. So here we have salt, okay, sodium chloride, and what happens when you put the salt into the liquid water? The water is represented by the big red dots with little gray dots, which in that video that we just watched, I like that he called them like Mickey Mouse ears. So when you add that in, what will happen is the water molecules will grab on to the individual chlorine ions. And remember that the chlorine ions are negatively charged because they got an electron from the sodium. So since this is negatively charged, the positive charge of or the positive side of the water molecule can grab onto it and bond to it. And then with the sodium is positively charged, right, because it lost an electron to the chlorine. And so now the negative side of the water molecule can bond to that. So essentially water can dissolve anything that is polar, meaning that it has a side that is negative and a side that's positive, or it can bond to or dissolve anything that is charged. Okay, and that's why it's so easy for things to dissolve in the water, and that's why we have salty oceans, right? Well, we talked about how they got salty, but the ability for them to dissolve into the water is really what gave it the ability to get salty. Okay. All right. If you guys have questions, please post them under the weekly discussion. Thanks.